Hi, my name is Albin Heimerson. I'm from Lund University, and I will present our work on automatic differentiation over fluid models for holistic load balancing. So I'm sure some of you have seen this picture before. There is no cloud, it's just someone else's computer. So I want to say it's not just someone else's computer. There is a bit more to the cloud. So in the cloud, we often have containers and VM to simplify creating and moving around things, and applications are often built using microservices. So each part of an application, the login, the ad delivery, are its own thing and can be moved around and scaled independently of the other parts of the application. This gives us a lot of flexibility in orchestration, and allows us to scale and move around things. And then the question is, how do we do this orchestration in an optimal way so as to minimize the cost of running this while also making the experience as good as possible for the user by not having long delays, stuff like that. So we view a distributed microservice application as something like this. We can have multiple different microservices here. Maybe the login is handled by the first one, and then the second one handles delivering a video to the user. And each of these can exist over several different sites. So we have maybe some edge nodes very close to the user, but they are more expensive to run and has less resources available. Local DCs, they're a bit further away, so the delay is longer, but they are cheaper to run and has more resources. And then centralized cloud, even more resources, but even further away. So the important thing is we have different delays and costs for the different sites, which creates an interesting optimization problem here. How should we distribute our jobs over these different things in order to create both the cost-efficient and a good experience for the user? And our control variables are these load balancing probabilities here. What is the probability of sending an incoming job to the different sites? So this work is based a bit on previous works where they looked at extracting fluid models from log data of these kind of applications. So it models each of these services as a multi-class processor sharing queue, where a job comes in here to the first microservice, and then we call it class 1, and then it sends it on to microservice 2, then it's class 1 on microservice 2, and then maybe it jumps back to microservice 1 to do some additional processing. But now the job is class 2 in microservice 1. So we have multiple different states on each microservice, and then within each class, we can also have different phases of the stuff going on. And this boils down to a fluid model then, where we see the jobs flowing through the network. And it looks something like this. Here we have all the different phases in the application. W here is the routing matrix, the internal routing matrix, and here is where the load balancing parameters come in. They affect how things are routed internally. Theta is a constraint on how much resources there are and how much work can be done based on the processor sharing for each job on each location. And lambda is the incoming jobs. So now that we have this model that existed before, our thought was, how do we use this to control well? And the easiest option to us seemed to be gradient descent. So if we take the model, simulate forward a bit, and based on some initial condition and load balancing parameters, then we define some loss function based on this state we achieved in the future. And we take the gradient based on this loss function with respect to the initial parameters. So the gradient has to traverse through the loss and then the solution. And this is not obvious how you should do by hand. So we would prefer to do this automatically. So our options are then to use numerical differentiation, but this is often inefficient, especially with many parameters and stuff like that. So instead we use automatic differentiation, since this seemed better for our case. The control, we pose a simple minimization problem here, subject to some constraints. So just some function based on the queue lengths on the different sites and microservices. We want to minimize some cost based on that, subject to that the model holds true and the probabilities are actually probabilities. And then we can add additional constraints here, such as the round trip time percentiles should be below some threshold. As long as our model can give us these variables, we can add anything here. To make this into something that we can actually differentiate, we don't want to work with the probabilities, so instead we work with a weight vector of real numbers, and then we just run that through a softmax function to get probabilities. We also put everything into a single function here. So here we have one part that checks the queue lengths, the cost of the queue, and then one part that is active when the constraint is broken, and then adds a cost here. So when we have a single function that we can take the gradient of with respect to these real weights. So now it's very simple. If we have automatic differentiation and implement this function, we can simply update our load balancing parameters by taking the gradient of this function with respect to our parameters. So our control loop ends up something like this. We run the environment using some parameters and collect data for 5 minutes in our case. We take this data, fit to our model. We take this model and simulate forwards and differentiate through this, find the gradient with respect to the parameters and update the parameters. And then we repeat this. It's a quite simple loop. So now to our experiments. The first experiment was offline. It used a single frontend and 2 backends, so we only needed to keep track of one probability, which allowed us to record data in a grid over this probability and just take steps along the grid points. This simplified also the visualization later on. Here we used a conditional cost function where if the threshold was broken, the part that drove down the response time was active. Otherwise, the part that drove down the queue length cost was active. So here we have the queue length, here we have the response time, and here we have the cost. The blue cost is the queue length, and the gray cost is the response time. We see that we start out here and move inwards. So blue is the recorded data, and red is the model moving and the model's prediction. So we start above the threshold. Thus, we start following the cost for the response time. And then as we go down below here, we switch to the cost for the queue and go all the way down here until we again hit the threshold, and the algorithm ends up bouncing between these two values. So we quickly found the minimal cost here, we see. The second experiment was a single front end and 3 backends. So now we use the weight vectors instead. And this was actually run live on real applications using 3 different Kubernetes clusters. Here we had a cost function where we incorporated both parts into the same equation using a barrier function. And we see again, here is the cost, that the cost goes down. And the blue area, we changed the load a bit. So we increase the load. We see a quick spike, but then it quickly goes down again and finds a good working point. Here we switch the costs and we see again the spike, but it quickly goes down. So we see that the algorithm quickly manages to find good working points. Yeah, so here's a summary. And I think that's all for me. Thanks for listening.